Good afternoon, everybody, and welcome to the second presentation for this afternoon's session at Linux Conference AU 2017. This presentation is by Tim Mithro-Ansel, and we'll be discussing using Python for creating hardware to record conferences, among other things. Thank you, Tim.
I do lots of things, so quick advertisement for another project I do, the Tomu board. If you want one, I've got 25 left. Please find me not in the middle of a talk while somebody's talking up the front. During the breaks would be better, especially not while I'm talking. So back to our main proceedings. I love Python. I love it so much. I started a conference about it here in Australia. But I'm also practical. I think you should use the right tool for the right job. I don't use Mercurial, I use Git because everybody uses Git. And everything isn't a nail as well. Like, sometimes it's better to use a screw and a screwdriver. And so, if you'd asked me a couple of years ago, should you use Python for hardware, I would probably have answered no. It's not the right tool for the job. But today, I say yes, and I'm going to explain why, and why I think you should too, why you should use Python for hardware. And I'll be giving a lightning talk on cool and awesome projects you should help with, some of which are Python hardware-based things later. So how did I get to this stage? We got to this stage through a project I started called the HDMI to USB, which is part of a bigger project called Tim Videos, which is aiming to record and live stream conferences like this one you're attending, to make it possible for people who can't attend to view it and hopefully in the future even participate. And so this is how you record and live stream a conference. Thank you, Katie, for making my horrible programmer diagram look semi-professional. The interesting thing is it's got Python pretty much everywhere. The mixing machine that does the combination and choosing between multiple feeds uses Python. The capture scripts are all Python. The streaming system that does the encoding, it's Python wrapped around C. The website, a Django thing, so that's Python. If you're at a Python conference, even the presentation's about Python, and some say my head's about Python. But there are two pieces of things that might not be Python, and that's these two things here called the HDMI to USB. Their job is basically to capture HDMI and DVI video sources to give you a nice, clean, crisp feed of what is going up on the projector. And the way we do that is we basically man in the middle, the presenter's laptop and the projector. And so we get a very clean, nice video feed of that. It appears, basically, the device appears as a UVC webcam and a serial port, and so that's how you capture it. And I can actually give a demo of that here. I've got my device going through a second capture thing, and what did I do with it? I have too many terminals open. Here, nope. Oh no, that's what happens when you loop a video back into itself through JPEG. But this is just MPlayer. If I actually move out of the way, you can see this is just an MPlayer window being fed into itself. So yes, this is kind of the capture. That's an MPlayer, and I can have a serial port as well this is kind of the console, and I can see what the status is. You can see there's one input, and it's connected out. Maybe if I make the terminal a bit bigger and what resolution it is. No drivers needed to make that work. What do I do with my slides? And so how does all this come together? The whole thing is based around an FPGA. And the great thing about FPGAs is that it makes hardware problems software problems. And I'm, at heart, a software engineer, and I like making mistakes which I can fix later. Hardware, you can't do that. But with FPGAs, we can continually improve the system. Every time we capture a conference, the system gets better because it's now software, and software improves as you go forward. The thing about FPGAs, though, is that they're software, but they're not really software. You can't just use Python directly on them. There are two major languages you use to program the stuff that goes on FPGAs, the hardware description. They're Verilog and VHDL, and neither of those are Python, sadly. So that's sad. But I said I was practical, and so I thought, okay, I will use what everybody else uses, Verilog and VHDL. And so I started working on this firmware, or more, I managed a person working on this firmware, because I don't have much time, and we got it mostly working. It did the matrix functionality, capture kind of worked, and it supported this dev board that we had. It was kind of slow, though. There's a lot of features on that dev board that we weren't using, like the Ethernet. It didn't do any type of buffering, so if you lost the signal, the output would also be lost. And the problem with VHDL and Verilog is that a lot of the stuff you use is generated by the toolchain that the vendor provides you. These have complicated licensing around them. They often say you can only use them on the chip that the manufacturer makes, so you can't use them on other things, which isn't really in the thing. It's not really open source if you can't reuse it however you want. And then we created some open hardware. This is the OPSIS board. Because our dev board wasn't open and we want the whole toolchain to be open, we created some new hardware, and so we needed to support this new hardware, and it had a bunch of more functionality. And the board, like our hardware, was kind of based around the same ideas as the prototyping board, but it was slightly different. And we need to refactor the code to make this work. And Verilog and VHDL made this really hard. We were having a lot of trouble supporting both boards. Then I came across this thing. This thing's called the Mixio. It has a very, very similar design to our board. Doesn't do capture, though. The interesting thing is that people who had developed that had written a system for describing the hardware on it that was called MeGen, and it already had a lot of components we wanted, like HDMI, DVI, DDR, and Ethernet, and it supported a lot of boards already, and it was Python-based. And so I thought, I was skeptical. Nobody else apart from these guys was really doing this. So I was still skeptical, but I thought I'd give it a try. And because I have no time, I instead made somebody else give it a try for me. So I funded Florent, who's actually here at the conference somewhere, and he did a rewrite, I'm going to say in approximately 4 weeks. He might disagree with that bit. And we ended up with a firmware that worked and did the things we wanted, plus a whole bunch of extra features that I hadn't asked him to do, that we kind of just inherited from him being more productive. It has buffering, it supported both the boards, has a soft core in it, and it has support for our Ethernet system. And so that's kind of comparing our old system and our new system. The new system was much better. And the other great thing is that we weren't using any of these blobs that had licensing problems. All of the stuff was truly available under a BST/MIT style license. So that was really good. And we're using it in production. Right here at linux.conf.au, we are capturing and live streaming the conference using the firmware that was developed as part of this. And so that's pretty awesome. But we're not the only ones. It's also been used at PyCon AU. It's been used at PyCons in America. And it's been used at DebConf in a couple of locations around the world. So this is truly something that multiple people are using, even if I happen to know most of them. So yay, Python. That got us to a system that we're actually using right now. But how did it do this? And I think that's a more important question. So let's dive deeper. The first thing is, writing hardware is hard. There are a lot more things to worry about. And you don't get things like being able to printf everything everywhere. You have to worry about synchronization because things happen all the time. And it's just hard, even if you're good at it. Writing hardware is also slow. The iteration cycles are slow. Even when doing it on an FPGA, the FPGA tool chains are slow. Sadly, they're mostly proprietary as well, so they're not getting any faster. And the type of problems they're actually trying to solve are hard. So they are quite slow, which means your iteration cycle can be on the order of hours. And that makes things hard. If you type make and then have to walk away for an hour, you're going to be much slower than if you type make and have to walk away for 5 minutes or 30 seconds. So that's kind of the frame of the problem. A couple of names that I need to kind of describe is that MeGen and MeSoc are two things that go together. MeGen is the Python kind of description thing, and MeSoc is the bunch of libraries that use MeGen to create their functionality. There's also this thing called LiteX, which is Florent's compatible soft fork of MeSoc that keeps a bunch of depreciated stuff and adds a bunch of experimental stuff that upstream is yet to approve. So I'm going to use these interchangeably throughout the talk. The problem you have with the Python HDL is that to convert it to run on an FPGA, the FPGA toolchains don't understand Python. And so we get around that by generating a language they do understand, which is Verilog. And so ultimately, you kind of think of MeGen as just an easy way to generate Verilog. It doesn't abstract away the hardware. You can't just write a piece of Python code and it automatically gets converted to hardware. You're still thinking about things like clock domains and gates and how signals combined. But it's much, much more powerful because Python is a high-level productive language. And so let's go through an example. In FPGA world, there are two types of things that happen. There are combinational things, which always happen. It's effectively like if you connect two pieces of wire together and you put a voltage in one end, you get the same voltage at the other end. Then there's synchronous things. You can think of them at every time a clock signal ticks, the thing updates. And so let's look at a blinking LED example. So this is a blinking module written in MeGen. The first thing is there's a counter which increments every clock cycle. So you can see the sync statement, counter equals counter minus 1. Sorry, decrements every clock cycle. So every time our clock ticks, it goes down by 1. And when it gets to the bottom, this being hardware, it just wraps around and keeps going. Then there's a combinational signal which connects the LED to basically the topmost bit of the counter, and that's the one that's kind of moving the slowest, right? And so this is a combinational signal, which means it's effectively consider a wire. So anytime that top bit is 1, the LED is on, and anytime that top bit is 0, the LED is off. And so this is what a LED blinker looks like in MeGen. And the reason I think this is better than the Verilog equivalent, which is about the same amount of lines, is because we're using Python, and Python is a powerful, productive language and can do things that are much harder in Verilog. Like this thing here. We define our counter to be big enough to fit our max cycles value. We don't have to define max cycles at the time when we're writing. We don't have to decide this thing's going to be 32 bits wide right now. We can decide that it's big enough to fit whatever value we pass in to this. And so if we pass in something other than the default 15 followed by a bunch of zeros, that signal will automatically shrink or grow depending on the value we want. And so that's really powerful. We can also do things like for loops. So we can connect multiple LEDs to the top thing at once. And we only get the signals. If there's one LED, it's functionally equivalent to the previous example. If there are 10 LEDs, there's 10 extra signals. And this is really, really powerful as well, because you can do if statements in your code which generate different code depending on your settings. And then the compiler that's taking the Verilog and converting it to the FPGA code doesn't need to try and figure out that you didn't actually need these things, because these things were never in the code it was looking at. So it can also be much more efficient. So as I said, Python is a powerful and productive language. It's why we use it for all these other things. And so using it as a way of generating Verilog and describing hardware is really good. However, while it's still Python, you're still writing hardware, and hardware is hard, and hardware is slow, and FPGA toolchains are slow, as I said. So let's reduce the amount of hardware we write. And the way we do that is by using a soft CPU. Soft CPU is basically a CPU implementation that we embed in the FPGA. And basically, it allows us to write C code instead of FPGA code. C code compiles the GCC. It's quick to compile, like a small C program can compile in milliseconds. It's quick to load onto the FPGA because we're only loading a very small amount. It gives you a very, very quick iteration cycle. And like the majority of the stuff you're doing, it's probably not required to run at extremely high speeds. Things like the command line interface. The human is not going to be typing at a bazillion characters per second. So writing a command line interface in C makes a lot more sense than trying to write it in Verilog or VHDL. And so this is one thing that's really powerful about MeGen and MeSoc, is that it gives you a soft CPU, but it also gives you all the extra bits that make interfacing to the soft CPU really easy, and it also gives you the choice of soft CPU. Like, not all soft CPUs are the right choice in the right situation. Some soft CPUs have better Linux support. Some soft CPUs are smaller and less resource intensive. And MeSoc basically allows you with a single line change to change which architecture you're using, and all your peripherals continue to work. It also generates the C code you need to talk to your peripherals. So you get C functions that let you read and write the registers you set up on your peripherals. It generates all these C code stubs. And so if we look at our blinking LEDs example in this world, we just use a GPIO register. And this is super powerful because our module is now one line. It creates a GPIO register that's connected to LED. And we get this I/O modules, LEDs write function generated in a C header that we can just call. And so if we want to make the LED flash twice as fast, we can update our C code, compile it, and load it in seconds. So this is really, really powerful way to speed up your development by doing more software and less hardware. And this is super, super powerful and super kind of a superpower that allows you to do FPGA stuff that you wouldn't otherwise be able to do. And it also has other benefits. We have a DDR controller that has DDR RAM connected to it. When you start up to get the DDR running and able to be used as memory, you first have to initialize it and train it. This is done once at startup. And it's reasonably complicated, like you have to do if statements and loops and these type of things. It's much easier to write that initialization in C than it is to write it in Verilog. You get these horrible giant state machines in Verilog to try and make this work. And they take up huge amounts of resources for something that's only done once. Whereas the C code, once it's done, you can discard it out of memory and use that memory for other things. And so it even makes you use less resources in your FPGA than you would previously, which is also really useful. It does have some downsides. You're going to need a compiler and you're going to need bin utils. There's also a smaller community, although I guess there's a bigger community writing C code than there is writing FPGA code, so that's an advantage. And you're still writing C, and C is not Python. So we're thinking in the future that there's this thing called MicroPython, which runs on CPUs. So why not write your firmware in Python instead of in C? And so this needs work. We're working on it. And these guys you should find and ask about it. That's Jim, Katie, and Joel. And they've just been volunteered. They don't know about that slide. But that's not the only thing. Inside our system on chip, we have the CPU. We have a bunch of memory interfaces like the ROM and the flash, and there's a wishbone bus that connects everything together. There's also a thing that connects the wishbone bus to the config status registers that configure your peripherals like your UART. And so this is kind of what is inside your FPGA. The thing is that the CPU in the FPGA is kind of crap. It's a 32-bit processor running at 50 megahertz, but I have a or probably 2 gigahertz Intel processor running on my computer. So why not use that instead? So the other thing that LiteX and MeGen give you is the ability to create a bridge to your host computer which lets you directly write into the Wishbone bridge that connects everything. And they have different ways to do that. You can do it over UART, which is kind of slow. You can do it over Ethernet, which is a gigabit. Or you can even do it over PCI Express if your car board has PCI Express. And this bridge has another advantage. This bridge then allows you to write Python code on your computer to write directly into the memory subsystem in your FPGA. And so this is what it looks like. On your computer, you're running Python. You can open a connection to it, and this is writing to that memory location too, and then you read it back. And I think I got my example wrong, but it looks like that. And so here's a bigger example. We're printing the memory map of what's in our FPGA. We have some ROM, we have some SRAM, and we have the main DDR RAM. And this is all Python scriptable on your computer using all the normal tools you want. And there's even tab completion. You get this w.regs object, which lets you write directly to the registers inside your FPGA, which have the same names as the C function. So this is previously the I/O LED module. So we can control that LED module from our computer and write one to that register, which would cause the LED to turn on. So I connected it up to IPython. So now we get tab completion and that type of thing. I can give you an example of that. I'd go here. No, Twitter, I don't care about you. So I have a thing, and I'm going to have to make my screen smaller. You can see that this FPGA has a certain amount of identifiers. It's running a Git revision of thing. It's HDMI to USB on our OPSIS hardware. And this is the memory map. As you can see, this one has a bit bigger memory map. It has SPI flash, it has Ethernet, and it has a JPEG encoder memory mapped. And here's my Wishbone object. And you can see that there's a regs object, and you can see that there's tab completion of all these different registers that I can write to. I'm not going to do that because my presentation is going through this. There's also a mems object that kind of gives you a list of the memory things, and I can do a Wishbone write, or I can do a Wishbone read. So this is a Python interface that when you're trying to figure out what the hell's going on with your piece of hardware is really, really powerful. If I go back here. But there's more. We can abuse this. The way HDMI USB works, it has a bunch of frame buffers in it. And so why don't we just write to those frame buffer locations from our computer? Let's see if this works. So if I connect to the terminal, I'm going to connect the pattern to the encoder. So now if I view this is the pattern buffer. It's got a little updating clock. This is MPlayer again. You can, see that my terminal is just hidden behind there. So let's quit that. And actually, I might connect back and connect the pattern buffer to the output. I must be connected to pattern. So that's there. And now, if I run my pattern upload, you can now see me writing directly to the frame buffer this image that I converted. And you can see that I haven't got the colors quite right yet. And if I FL... You pirated my photo. Yep. I can connect the input to the output. Again, this is kind of what it looks like on the computer. Again, we have a little bit of GStreamer magic to convert it to the right format, but you can see the memory map that we had previously, and I just have a Python progress bar to write it down, because despite it being gigabit Ethernet, there is a bit of overhead in writing directly to the memory bus in the side the FPGA. So that is really powerful. But it's even more powerful in another way. FPGA toolchains are really slow at the best of times. And that's because FPGA toolchains are trying to solve a hard problem. It's an optimization problem. You've got this description of the hardware that it has to map into basically this grid of stuff that implement it. And the more stuff you're trying to map onto the grid, the harder it is to fit everything into the grid. And so the bigger your system is, the longer it takes to do this. And it's kind of an exponential thing in that the fuller your FPGA gets, the longer it takes. And for big systems fitting on small FPGAs, it can take hours to try and compile. So let's reduce the hardware on the FPGA. And so I described this earlier. And so say we're working on a peripheral up the top. This peripheral normally connects via this wishbone bus and has some CSR registers. So really, why don't we just have a bridge and a peripheral in our FPGA? Because when we're developing this peripheral, we don't care about the UART or the DRAM controller or any of these other things. We just care about the peripheral we're working on at this time. And so by having this bridge, we can make our thing we're developing really, really small, which means it's really fast to compile, because normally your FPGA has all this other stuff in it, but now it's just got your peripheral. And so this is another huge advantage that this Python system gives us, is that we can develop this peripheral and have much faster iteration cycles, because we have this ability to bridge and control the peripheral from your computer. And we could use Python to do the poking of the registers and setting up and all those type of things. So in summary, writing hardware is hard. It's also very slow, and FPGA toolchains are slow. So what we want to do when developing hardware so that we can iterate quicker is we want to reduce the amount of hardware we write, full stop, and we want to work on small bits at a time. And these two things are why Python and MeGen and MeSoc LiteX are so powerful and able to do so much with so little resources. Python itself is a really productive language. It gives you a soft CPU that allows you to write stuff that isn't critical to be in the FPGA, not on the FPGA. And it gives you these bridges which allow you to do a lot of development on your computer rather than on the FPGA, where you don't have things like printf. And it also allows you to have these bridges which allow you to develop small units at a time rather than developing the whole huge thing at once. These aren't all unique to MeGen and MeSoc. There are lots of other systems that try and give you this, but MeGen and MeSoc and LiteX is the first one that I've come across that I'm able to use as a person who understands Python and a bit of hardware. So yeah, that's why MeGen and MeSoc and LiteX and using Python for hardware development, I think, is really important. But there's also more. There are two competing standards for doing Python in FPGA land. We're using MeGen. There's also this myHDL. We can also use Python in other parts. Schematics and printed circuit boards are two things you need when creating open hardware. We use KiCad, which is a totally open source tool to develop these. And we use it to develop the FOSS, which is fully open source, published on GitHub, the full source code, PCB source code. The great thing about KiCad is it's scriptable by Python. As well, the KiCad formats are all plain text, and Python is really great at plain text. And so FPGAs, because they're configurable, let you connect anything to any of the pins, but on a circuit board, your pins are hardwired to certain peripherals. And so you need a file that tells you what the FPGA is connected to. So I have a Python script that takes the schematic and generates that description. So it means that we're not going to have a translation error from converting from the schematic to the UCF description, because it's done automatically. And we can add checks so that we know that the right pins are connected. Like some pins can only do certain functionality. We can check that, which leads to the next thing. We should have circuit unit tests. It would make developing hardware much quicker if I could check all these rules that I do by hand, like the fact that HDMI can only be connected to certain pins on the FPGA. That seems like something that my tooling should check for me. So you can use it to actually help you really build hardware. As well, there's another library which lets you do things like check your trace lengths are matched and that type of thing. Project Gus wrote that, and I've improved it. So, but there's even more. Once you have hardware, you have to talk to it. There are two main interfaces to talking to hardware: USB and serial, and Ethernet, I guess. PyUSB is a great thing for talking to USB devices if you don't want to write a full C driver. It's pure Python using C types. So you just need one of the libUSB libraries somewhere on your computer. It supports Python 2 and Python 3, Linux, Mac, Windows, BSD, I guess. I don't know anybody who uses BSD, so. And it lets you write low-level drivers talking USB. You don't need drivers on Linux, but you might need to run it as root. On Windows, it's mostly fine if you have a tool that generates some stubs. I have no idea on Mac or BSD again. We use it here on our OPSIS to manage the fact that our USB chip is also programmable and can operate in a whole bunch of different modes. And so that was really useful. We use PyUSB to detect the board and switch the modes from different types. Most of the time, though, you don't need USB. The USB is just a serial port. And Python also does serial really well. So that's pretty great. Again, PySerial has support for things like Jython and IronPython. So that's kind of cool if you're crazy enough to use those things. Again, Windows, Mac, and Linux support. And it gives you kind of a read-write interface to your serial port. And so, yeah, we could use PySerial for controlling this board, the HDMI USB board, if we wanted. You could write a little GUI for it. We'd love some help with that. I believe Ryan has been working on that this conference. So yeah, that's basically it. We want to make presenting, recording, and live streaming be reliable and easy. And one way to do that is to make it all open source so that we can fix the bugs so that next conference you don't have the same issues. And so that's why I'm doing this. But we need your help. There's so much more we could do. If you have any interest at all in FPGAs, in Python on FPGAs, in Linux kernel development, embedded development, we could probably find something for you to do. Or if you're just a Python person and want to do things like create us a GUI to control the HMISB, that is something we'd love your help with. You don't need hardware to do a lot of the things, and I've also been known to send people who contribute hardware because my employer pays me too much, and I don't have any other hobbies. So yes, and here's a video of what it looks like when it goes wrong. So on that, I'm finished. I bet you the Nock's freaking out about my video being out of sync now. So yeah, do we have time for questions?
We have time for a few questions.
Okay, I did not expect that.
And please make sure that they are questions. If they're not questions, I will cut you off.
You mentioned the proprietary nature of the FPGA vendor synthesis systems and stuff. Your the MESOC system obviously generates Verilog, which I'm assuming you're still feeding through the proprietary FPGA synthesis engine.
Yep.
You've also got peripherals.
Yep.
Has MESOC implemented their own IP blocks for those peripherals, or are you still leveraging those that are provided by the vendor-supplied synthesis?
We basically, all the peripherals we use, MESOC or LiteX have implemented totally themselves, so we're not using any vendor-provided IP. We still need the toolchain to do the compilation. I'm hoping that Clifford Wolf in Austria has been doing a bunch of work to make it possible so that we don't need their toolchain. I've been following his work closely. He has the Lattice FPGAs working. They're much smaller than what we need for our system. But he did announce that he would be working on some more advanced FPGAs this year, and so I'm looking forward to that. But we also don't use like the memory controller that Xilex provide. We have our own memory controller, and our own memory controller actually uses a lot less resources than the Xilex IP does, and same with our HDMI controller, uses a lot less resources than the Xilex provider. It's kind of funny how a person who makes money selling you larger FPGAs gives you systems that use lots of FPGA resources.
So I guess, so just to sort of wrap that up then, for the specific IP blocks that the MESOC people have implemented their blocks for, you're cool. But if you are using if you're trying to generalize this and you're using other FPGAs with other peripheral mixes, or you're using peripherals that you're not using or they haven't implemented, then you've still got to fall back to the proprietary ones. Like their coverage wouldn't be 100% over every FPGA, right?
No. A lot of our stuff supports Altera FPGAs and the higher end Lattice stuff, and MeGen itself does support the open source toolchain. It's just our stuff doesn't really fit in the small things. But yeah, if we don't implement a core that you need, you're going to have to either wrap the existing one, which is actually pretty easy to do. Our soft cores are actually written in MeGen. They're existing Verilog implementations that are fully open that we wrap. That wrapping process is actually very easy, and another thing that's really powerful about MeGen is that you can wrap these interfaces easily. Some of the other tools and non-Verilog HDLs have a problem interfacing with Verilog cores and stuff like that, whereas we can do it quite easily.
And with that, we are out of time, I'm afraid. Thank you again to Tim, a small gift
Thank
from
you.
the organisers of Linux Conference AU, and thank you very much.